Somewhere over a California test range, a fighter-sized aircraft climbs into the sky with no one inside it. No pilot. No cockpit. Just a machine making its own decisions in real time. This is America's newest weapon, and it could change the way wars are fought. But 8,000 miles away, in a hangar most of the world will never see, engineers are trying to build the exact same thing. Not from scratch. From what they've already learned by studying America's last stealth drone, piece by piece. The question isn't whether China can copy this technology. The question is how close they can get, and what happens if they succeed. To understand that race, we have to go back to the night one of America's most secret aircraft simply disappeared. In December 2011, an American reconnaissance drone was flying quietly over the border region near Iran. It was the RQ-170 Sentinel, a bat-winged aircraft so secret the U.S. Air Force had barely acknowledged it existed then. Without warning, contact was lost. Days later, Iranian state television aired something stunning. The Sentinel, sitting almost fully intact on Iranian soil. American officials said it had malfunctioned. Iranian officials claimed they had hacked its systems and guided it down. Whatever the truth, one fact could not be undone. A machine built to stay invisible was now sitting in the hands of a rival government. Within days, reports emerged of a foreign engineering team arriving in Tehran to examine the wreckage. According to multiple aviation researchers, that team was reportedly Chinese. This wasn't China's first attempt to shortcut decades of research through reverse engineering. Back in the 1950s, after a split with the Soviet Union, Chinese engineers began taking apart Soviet target drones just to understand how they worked. That pattern, study first, build second, became a foundation of China's aerospace program. So when photos began circulating online of a new Chinese aircraft with the same swept, tailless silhouette as the missing Sentinel, few analysts were surprised. It wasn't proof of an exact copy, but it was a signal that the blueprint had traveled. And it set the stage for a much bigger contest, one playing out in plain sight today. To understand why this technology is so hard to copy, you first have to understand what makes it invisible. A stealth drone isn't hidden by magic, it's hidden by geometry. Its flying wing shape has no vertical tail, no sharp angles, nothing to bounce a radar signal straight back to the sender. Every surface is designed to scatter incoming radar waves away, instead of reflecting them home. The skin of the aircraft is coated in radar-absorbing materials, developed through decades of classified research. Even the engine is hidden, buried inside the fuselage, with the exhaust shielded so heat-seeking sensors can't easily find it. None of this works if just one detail is wrong. A slightly different curve, a mismatched material, an exposed seam, and the whole stealth profile can fall apart. That's the real challenge in copying a drone like this. It's not one secret, it's thousands of small ones working together. You can photograph the outer shape in a parking lot. You can't photograph the alloy inside the panel. And beyond the physical shape, there's something even harder to replicate: the software. Modern stealth drones increasingly fly themselves, using autonomy systems that make decisions without constant human input. That code, refined over thousands of test flights, may be the most valuable part of the whole aircraft. Which raises the real question at the center of this story. Can you copy the shape of a weapon without copying what makes it actually work? In August 2025, that question moved from theory to reality. General Atomics flew its YFQ-42A, nicknamed Dark Merlin, for the very first time a jet-powered, uncrewed fighter built for America's new collaborative combat aircraft program. Just weeks later, Anduril's YFQ-44A Fury took to the sky as well. These weren't just drones. They carried an F for fighter in their designation, the first uncrewed aircraft in history to earn that label. Their mission: fly alongside crewed jets like the F-35, acting as autonomous wingmen that can scout, strike, or absorb risk a human pilot wouldn't take. And the price tag stunned defense analysts, each aircraft targeted at under $30 million, roughly a third the cost of a single F-35. By mid-2026, both designs had moved from prototypes into full production, rolling off assembly lines in Ohio and Arizona. For the U.S. Air Force, it was proof that a machine could go from first flight to factory floor in under a year. But across the Pacific, China wasn't standing still. Its own stealth drone, the GJ-11 Sharp Sword, had already been flying in prototype form since 2013. By 2019, it appeared publicly for the first time, its flying wing shape drawing immediate comparisons to America's B-2 bomber. Then, in 2025, it reappeared at a military parade, this time with something new. Folding wings. Folding wings mean one thing in military aviation. This aircraft may be designed to launch from a ship. Analysts began connecting the pieces. A wing profile that matched the emblem of China's newest amphibious assault vessel. By early 2026, imagery reportedly confirmed a naval version, complete with a catapult launch bar and reinforced landing gear. If accurate, it would give China something the United States doesn't currently have in service: an operational, carrier-launched stealth combat drone. For the first time, the race wasn't just about who could build a stealth drone. It became a race over who could get one to sea first. So why does any of this matter beyond a runway or a flight deck? Because these machines could reshape how nations think about risk in a conflict. A crewed fighter jet represents years of training and a human life on board. An uncrewed drone represents neither, which could change how willing a military is to send one into danger. For the United States, drones like the YFQ-42 and YFQ-44 are being designed to fly ahead of manned aircraft, scouting threats before a human pilot ever gets close. In theory, that could make missions safer for the people still flying inside the cockpit. By 2019, it appeared publicly for the first time, its flying wing shape drawing immediate comparisons to America's B-2 bomber. Then, in 2025, it reappeared at a military parade, this time with something new: folding wings. Folding wings mean one thing in military aviation. This aircraft may be designed to launch from a ship. Analysts began connecting the pieces, a wing profile that matched the emblem of China's newest amphibious assault vessel. By early 2026, imagery reportedly confirmed a naval version, complete with a catapult launch bar and reinforced landing gear. If accurate, it would give China something the United States doesn't currently have in service: an operational, carrier-launched stealth combat drone. For a navy focused on projecting power across the Pacific, that capability would be significant. For the first time, the race wasn't just about who could build a stealth drone. It became a race over who could get one to sea first. That distinction matters more than it sounds. So why does any of this matter beyond a runway or a flight deck? Because these machines could reshape how nations think about risk in a conflict. A crewed fighter jet represents years of training and a human life on board. An uncrewed drone represents neither, which could change how willing a military is to send one into danger. For the United States, drones like the YFQ-42 and YFQ-44 are being designed to fly ahead of manned aircraft, scouting threats before a human pilot ever gets close. They could also carry weapons, act as decoys, or relay data across a battlefield. In theory, that could make missions safer for the people still flying inside the cockpit. For China, a carrier-capable stealth drone could extend its reach far beyond its own coastline. That kind of reach has long been a strategic goal for its expanding navy. It could operate from ships in contested waters without needing a nearby runway on land. For defense industries, this shift is already reshaping how aircraft get built. Instead of one exquisite multi-decade jet program, companies are now racing to build fleets of cheaper, faster, expendable aircraft. Some analysts believe future air forces may include hundreds of these drones for every crewed fighter in the sky. That changes the economics of an entire industry, from parts suppliers to training programs to how wars might be fought. And for ordinary people far from any battlefield, the ripple effects reach further than most expect. The same autonomy software being tested in these drones could eventually influence self-driving systems, delivery robots, and civilian aircraft. Stealth-grade materials research often finds its way into commercial aerospace years later. Every leap in this race, in other words, doesn't stay contained to the military alone. History suggests today's classified project often becomes tomorrow's everyday technology. But before anyone declares a winner in this race, it's worth asking a harder question. Does copying the outside of a machine mean you've actually copied what makes it dangerous? Most defense analysts say no, and the gap may be larger than it looks. A radar-evading shape is only the first layer of stealth. The materials underneath matter just as much, and those recipes are among the most guarded secrets in aerospace. Engines are another barrier. Building a reliable, high-performance turbofan is one of the hardest problems in all of engineering, and it can take decades to master. Historically, this has been one of China's most persistent weak points, even as its airframes have advanced quickly. Then there's the software, the autonomy systems that let a drone fly, decide, and react without a human hand on the controls. That code isn't something you can photograph off a parade float. It has to be built, tested, and refined through thousands of real flights. The United States has spent years running exactly those tests, using systems like Collins Aerospace's Autonomy Suite and Shield AI's HiveMind on its own CCA drones. It's unclear how much flight testing data China's newer drones have actually accumulated, since much of that information isn't made public. There are also basic questions about reliability. Even America's own prototypes haven't been flawless. 1. CCA test aircraft was paused earlier in its program after a crash. If the most advanced military in the world still runs into setbacks, it's reasonable to expect any competitor will face the same. Cost is another quiet challenge. Building one impressive prototype for a parade is very different from mass-producing hundreds of reliable, combat-ready aircraft. And there's the secrecy problem itself. Outside analysts are often working from photographs, parade footage, and speculation, not verified specifications, which means some of what looks like a finished weapon may still be in reality an early-stage demonstrator. The uncomfortable truth is this: nobody outside a small circle of officials in Washington and Beijing knows exactly how close this race really is. That uncertainty is, in some ways, the entire point of keeping these programs classified. So where does this go from here? In the United States, the next phase of the Collaborative Combat Aircraft Program, known as Increment 2, is already being planned. Future designs could be built with even greater autonomy, potentially allowing groups of drones to coordinate as a single team with minimal human input. Researchers are also exploring how these aircraft could operate in swarms, sharing sensor data, and dividing tasks among themselves in real time. If that technology matures, a single human operator could potentially oversee multiple drones at once, rather than one drone per person. On the other side of the Pacific, China's naval variant of the Sharp Sword may still be years from full operational status. Reports suggest it could eventually pair with China's newest stealth fighters aboard its largest aircraft carriers. Chinese researchers are also said to be developing their own AI-driven swarming algorithms, though independent verification of their maturity remains limited. Neither country has confirmed exactly when these systems will be fully combat-ready. What both nations agree on, at least publicly, is that uncrewed aircraft are no longer a side project, they're becoming central to future air power. That shift alone could reshape defense budgets, alliances, and military strategy for decades. Allied nations are watching closely, weighing whether to invest in their own uncrewed fleets. But technology like this rarely stays contained to just two countries for long. Other nations are already watching this race closely, and some may attempt to follow either blueprint, which means the real future may not be a two-country contest at all, but a much wider, harder-to-predict competition. Smaller nations with limited budgets may find drones a cheaper path to air power than fighter jets ever were. And that possibility raises questions far bigger than any single aircraft. Strip away the parades, the press releases, and the grainy leaked photographs, and one theme remains. For over a decade, a single lost aircraft in the Iranian desert has quietly shaped an entire arms race. One nation is trying to protect an advantage it spent decades building. Another is trying to close that gap as fast as it possibly can. And caught between them is a technology evolving faster than most people even realize. Somewhere right now, an engineer in California is running one more test flight before sunset. Somewhere else, another engineer is staring at a screen, trying to make sense of a shape in a photograph. Neither of them may ever see how this story fully ends, because the truth is, this isn't really a race to build the better drone. It's a race to answer a much older question: who gets to define the future of war? And for now, that question remains wide open, 30,000 feet above us, in the shape of an aircraft with no pilot at all,